ठीक है. Hello, students. So, welcome to today's session. Uh, as indicated in the agenda, we would be, discussing today about how to solve electrical circuits. And when we are saying how to solve electrical circuits, today's focus would be to find out the equivalence resistance when multiple, resistance or resistors are in series and parallel in an electrical circuit. So, uh, just give me a moment. So, so we know that yes, in our this session for class 12, we are yet to discuss on electric current as a physical quantity and obviously understand the other theories related to this. But I believe that in Gauss law we have discussed a lot of theory, and then most of the practice problems were also requiring a lot of symmetry and imagination. So this one I thought, let's start with some problems, then we would enter into theory. And today's entire discussion would be all around solving a lot of things, practically. So, it would be like your practice problems. And for sure, be it your board exam, be it your competitive exams, in some form or the other, you can expect questions from this. Okay. So, the aim of, so as we said, right, so we would be trying to find out the equivalence resistance, right? Equivalent resistance in a given electric circuit, right? So let's begin this with just this much a formula that in high school studies we have studied V equals to IR, right? And that here, obviously, the symbols means this stands for your potential difference. This stands for electric current, and this stands for the resistance of the resistance, right? So yeah. So which means suppose I connect I connect a bulb in an electrical circuit. Say I attach a cell to the bulb, assuming that this produces a potential difference of 5 volt. Okay, and assuming the resistance of this electric bulb is 1 ohm, right? So we can say that the current in the circuit that would go through in this closed loop like this would be I would be equals to V by R, that is nothing but 5 volt by 1 ohm, that is nothing but 5 ampere. So we know this thing, from our high school studies, and we have studied Ohm's law, which proves V equal to IR. We will get into the details of them later. But today, what we want to know is, say, it is very unlikely that in an electrical circuit there would be only one electrical equipment, right? So most of the times, let's take the example of the room where you are sitting, right? So obviously in that same circuit you have your fan attached, you have your light attached, you have probably your AC attached, and many other equipments, correct? So in reality, many times what happens, rather than having one device here, probably suppose one more device could be connected. Okay, and then there could be one more device connected here in some way. So, in reality, there could be multiple electronic devices, electrical or electrical devices connected in a circuit. And when suppose this one has a resistance R1, this one has a resistance R2, and this one has a resistance R3, right? So suppose this is 1 ohm, this is your 2 ohm, and this is 3 ohm, right? In this scenario, if I were to apply this Ohm's law V equals to IR, so what I need, the total potential difference, the equivalent potential difference is 5 volt. But what I don't know is what is the equivalent resistance of these three devices, which are which are arranged in a particular spatial arrangement. What is the equivalence resistance of that? This part we don't know. So if we can find it out, for sure we can find out what current is flowing at the start of this cell, right? So that we can find out. And our today's all the problems that we will be solving, we would be trying to find out the R equivalent in different cases or different scenarios. Okay. Now let's move one step forward. Okay. So so remember students, so all these electrical, you're in an electrical circuit, the uh, equipments or the electrical, resistance, it could be set up in either of the two ways, right? So two registors, two registors can be either in series or in parallel. Okay, two registers can either be in series or in parallel, and we need to find out whether they are in series, whether they are in parallel, and then find out the equivalent resistance across them. Okay, so here I'm not doing much of deductions because the aim of today's class is more to go through the practice problems. We will be covering all the theory part of it in the next class. Okay, so for today's class, we can understand that. Okay, let's start understanding what does the it mean by saying two registers are in series. Okay, so say in an electrical circuit, and this is how a resistance is indicated in circuits. So we have one resistor, we have the second resistor, and if they are connected like this in an electrical circuit, R1 and R2, obviously current I would start from here and flowing and coming like this, right? So if there are two resistors connected like this, they are said to be in series. Okay, okay. And the classical definition says if current through two resistors are same. I repeat, the classical definition says if current through two resistances are same, those two resistances are said to be in series. Similarly, if we go to the definition of parallel, it says, suppose we have one register like this, another register like this, and we connect it to a cell. Okay. In this situation, R1 and R2 are said to be parallel to each other. And the classical definition again says that when potential difference across two registers or two resistances are same, then they are said to be parallel. So if current is same, then they are said to be in series. Okay. Now this is the classical definition. We would go into my definition in a couple of minutes. Okay, and that will help you solve a lot of problems. Okay, now let us quickly note down one formula which we would use for series and parallel. Okay, series. So if two registers are in series, say this is R1 and this is R2, then their equivalent resistance is always the summation of both the resistances. So which means if you have a battery here or a cell here, you apply two resistors in series, both of their resistance would be added and they would produce that much of added resistance to the cell. Okay. Similarly, when they are in parallel, the equivalent resistance across them, req, would be equals to r1 into r2 by r1 plus r2, and this is derived from a formula that is 1 by r equivalent equals to 1 by r1 plus 1 by r2. Okay, we would see these deductions in the next class, but today we are gonna concentrate on the problems related to this. Okay, so we will use these two formula number one: if in series, add the resistances; if in parallel, r1 r2 by R1 plus R2. One more small formula. So say if three registers are in series, R1, R2 and R3, then R equivalent would be R1 plus R2 plus R3, right? And assuming if each one is R, then your R equivalent would be R plus R plus R, that is nothing but 3R, right? And similarly, if two resistors are in parallel and both values are equal, then your R equivalent would be how much? Your R into R by R plus R. So that is nothing but R squared by 2R, or that is nothing but R by 2. Okay, and we can extrapolate it. We can extrapolate it that if n number of registers are in parallel, then R equivalent would be R by n. Okay, so we would just use these formula in our today's discussion. So when multiple registers are in series, add them, and if all of them are equal, it would be R equivalent would be NR. And if n number of resistors all are in parallel, then equivalent resistance would be R by N. Okay. Now let us get into the problems. Okay. So let's start up with a very simple, one. Okay. So let's start with a very simple one. So say we want to find out what is the equivalence resistance of this circuit. So I have a okay. I have two registers like this, okay, and the third register is like this, okay. This is say R1, this is R2, and this is R3, and I'm saying find out the equivalence resistance across points A, B, which means though I have not shown it in picture, so assume that this is connected to a cell, okay, and in problem we want to find out the equivalent resistance across these 2 points. Okay, so let me erase it for our purpose. We don't need it right now, okay, because we are not calculating the current and all those things. Okay, so let us try to find out equivalence resistance in this case. Okay, so let us now come to my model of finding out series and parallel. Okay, so please note it clearly, carefully. Series. So whenever we are trying to find out series and parallel, point number one: always always do it always do it in a group of two resistances. Okay. Okay, so basic series or parallel, we'll always try to find out, by taking a couple. So that's why I have coined that term, lovers couple versus, happy spouse. Okay, so I draw an analogy that two resistors that are in series, they are like a lovers couple. Okay, what does it mean? At the meeting point of these two registers, if any third register gets joined, so these two would cease to be in series. So suppose if I add one more register here in the circuit, okay, okay, initially this was the case, right? So we could say that R1 and R2 are in series because at their meeting point there are two and only two. So these two are a good lovers couple. They don't have any third person interfering into their relationship. Their relationship is going great. They are in series. Okay, but the moment a third register gets added, okay, they would cease to be in series. Now I cannot say that R1 is in series with R2. Does it mean that R1 is in parallel with R2? No, the answer is no. We need to find out. We cannot right away say that if not in series, they are immediately parallel. We need to find it out, and we would see it through different problems. Okay, but remember, students, when two registers uh, are connected, and if at their junction point it is only those two and no third element in the circuit, then and only then they are in series. Okay, so that only makes them a happy lovers couple, and they are in series. Now let us go to the parallel model. Okay, parallel. So two registers two registers are said to be in parallel when they have a complete loop with them. Okay, so I have R1, I have R2. By taking two registers, if I can make a complete loop, I repeat, if by taking two and only two registers I can make a complete loop, then they would be in parallel. And that is how I drew that analogy, that when you have whenever you have a happy spouse, right? So or any happy married couple, they don't mind if suppose a third one is over here, right? But still I can say R1 is parallel to R2 because just by taking R1 and R2, I can close a loop. So their world is complete with just R1 and R2. So they are a happily married couple. Similarly, if this is R3, then R1 is also parallel to R3, right? So R1 and R3 are also in parallel because just by taking these and only these two, I can complete the loop. Okay, so these are the key points. A, if at the meeting point there is no third, register, then they would be in series. If by taking two and only two registers, I can complete a loop, they would be said to be in parallel. Now, with these fundamentals, let us start solving our problems. Okay, so let's start with the first one. Okay, so in this circuit, right now, this is very simple. So R1 and okay, so can I say that R1 is in series with R3? The answer is no, because R1 and R3, I can assume that they are meeting at this point. So if R1 and R3 are meeting here, there is this disturbance R2. So a third one is also connected. So I cannot say that R1 is in series with R3. Similarly, R2 is also not in series with R3. Okay. So obviously, and to start with this circuit, I cannot say that which two are in series. Okay, now, but if we see here, if I take only R1 and R2, I can complete this loop, right? So which means I can say R1 is parallel to R2. Okay, if R1 is parallel to R2, can I say that this circuit reduces to something like this, that will have one resistor here whose value would be R1 R2 by R1 plus R2. So we have just taken the formula number 2, which we had seen for equivalence resistance, right? R1 R2 by R1 plus R2, and then you have R3 here, right? So first thing, R1 and R2 are parallel, right? And this entire parallel thing is in series with R1. So now the circuit is resolved, right? So now we can find out the equivalent resistance. So the answer would be R1 R2 by R1 plus R2. And then if it is in series with R1, so equivalent resistance would be plus R1. So this is nothing but your total equivalent resistance. Okay. Now, if yes, yes, okay, and if this is a total resistance, now to simplify, so say if you want to work out your numericals also. So say if I say this is 10 ohm, this is 10 ohm, okay, and this is also suppose your 10 ohm. So in this scenario, these two are in parallel, so it would be 10 by 2, that is 5. So 5 is in series with 10 ohm. So 5 plus 10 equals to 15 ohm would be the answer in this case. Okay. Now, now let us. This was a very simple one to start with, and we will keep increasing a bit of complexity as we move on. Okay. Now let us go ahead and solve a little complicated one. Okay. So say we have one register here. Okay, and then we have a structure like this. Okay. So from here we go like this. From here we come like this. Okay, and I'm saying find out the equivalence resistance across these 2 points A and B, and I'm giving, for example, say everything here is, suppose your 5 ohm, or for simplicity let's say this is 5 ohm, and let us say this is 6 ohm, this is 6 ohm, and this is 6 ohm. So what will be the answer? The answer would be 7 ohm. So just by looking at the circuit, we can say that the answer would be 7 ohm. How? Let us start, solving. Okay. So can I say that this one and this one is in series? Answer is no, because at the junction point there are so many disturbances, right? So these two cannot be the happy lovers couple, so they are not in series. Similarly, you don't have any such couple in this, circuit, so no two registers are in series directly. But taking these first two registers, see, we can complete a loop, right? So that is why we can say that this and this. Okay, now let me do the numbering. 1, 2, 3, and 4. So what can I say? 2 is in parallel with 3, because taking just 2 and 3 and nothing else, I can complete a loop. Yes, there is one more thing here, but that doesn't matter. As long as we can complete a loop by taking 2 and only 2 registers, they are a happy married couple, so they would be in parallel. Okay, so 2 is in parallel with 3. And this entire thing, so whatever becomes the resistance of that. So if 2 and 3 are parallel, so can I say that this is 6 ohm, this is 6 ohm? So the parallel of when I want to draw the equivalence, it will be 3 ohm here, right? So it will be 3 ohm, and if that is true, I can remove this, right? Now again, or yeah, and then this is again parallel, so these two are parallel, and finally these are in series, so you get the answer. So these two are parallel again. 6 into 3 by 6 plus 3, so this is 2 ohm. So that is how we are getting 2 ohm here. There is a 5 ohm. So once this has come to this 2 ohm, the circuit would have shrunk to something like this. Now the circuit would have been like this: 2 ohm, this, sorry, 2 ohm, which is nothing but 2 parallel to 3 parallel to 4. Okay, the equivalent resistance of that is 2 ohm. Now if we see, these two are now a happy your happy spouse, sorry, your happy lovers couple, so they don't have any disturbance among themselves. So the answer will be 5 plus 2, 7 ohm. Okay, very simple. Now, so that's why we always say that your electric circuits are like your niches. Okay, they look big, they look strange, but they shrink very quickly. Okay, now let us go to problem number 3. We would just take the same one and increase the complexity slightly. So one register is like this, the second register like this, then we have like this, then we have like this. We have one here, we have one here, we have one more here. So say register number one, two, three, or one, two, three, four, five, six, seven, and assume every register is nothing but your R ohm. Doesn't matter whether they are in the same values or different values, right? So we just trying to understand the concept here. Okay. Okay. Now in this case, if you see, let us try to first find out the series. Okay. So step number one. Can I say that two is in series with three? Say between two and three. This is the junction point and there is no disturbance here. So which means 2 and 3 are in series, right? Similarly, can I say that 5 and 6, these two are in series, 5 and 6. So if 5 and 6 are in series, right? So these two are there, right? So if these two are in series, so can I write that if this is R and this is R, so rather than showing them as two different registers, can I show them as one single register, two are here, right? Similarly, here also 5 and 6 are in series because this is the meeting point of 5 and 6. There is no disturbance here. There is no third element. So which means 5 and 6 are in series. And that's why I can say rather than saying 5 and 6 R and R, I can put an equivalence register of 2R here, right? So now 2R and this is R. Okay. Now if we see these three are in parallel, so you can just find out this is in parallel with this. So you can just reduce all these three are parallel. So or you can reduce them together, and then these two are also in series 1 and 7. So let us find out if these three are in parallel, then what is the value. Okay, so 2R and R are in parallel, so it would be 2R into R plus 2R plus R, which is nothing but 2R squared by 3R, 1R, 1R gets cancelled, so this is nothing but 2 by 3R. Okay, so now for these two 2R and R, I can rather write one register, which is nothing but 2 by 3R. Now, these 2 by 3R and these 2R, they are again parallel, right? So 2R into 2 by 3R plus 2R plus 2R by 3. So solve it, whatever you get, we'll find it out. So yeah, so it will be upstream, this is 4R squared by 3, and here in the denominator this is 3, and here you will get 6R plus 2R. So these three get cancelled out, right? So this becomes 4R squared by 8R. 1R gets cancelled out, right? And this will be 2. So that is nothing but R by 2, right? So rather than saying all these three parallel things, right? I can now replace this entire thing with a register whose value is nothing but R by 2. Now, now this is parallel with now this and this. All these three are in series because this and this is in series because at the meeting point there is no disturbance. This and this is in series. At the meeting point there is no disturbance. We have seen in formula number 3 if you have multiple registers in series, then obviously the equivalence resistance would be the addition of all of them, right? So R plus R plus R by 2, that's the answer, right? So it's nothing but if you take 2, so you can say 2R plus 2R plus R, that is nothing but 5R by 2 or 2.5R. Okay? Yeah, pretty simple. So let us move on to the next one. Okay? Let us move on to the next practice problem. Okay? Yeah. So now let us try to solve this. Okay? So suppose we have letter A and we have made an electric circuit like this. Okay, okay, and assume all the registers are again R. Okay, and let us give the numbering 1, 2, 3, 4, 4, and 5. And I'm asking what would be the equivalence resistance across these 2 points A and B. Okay, we'll follow the same principle. Okay, first step, the ones which are in series, let us try to find them out, add them so that my circuit will start getting strength, right? So here straight away I can say that 2 and 4, 2 and 3. So can I say 2 is in series with 3? Again, the same reason, find out their meeting point. This is their meeting point. At their meeting point, is there any third disturbing element? No, there is no third disturbing element. If there is no third disturbing element, then they are, you're happy, lovers couple, or they are, you're in series. So 2 is in series with 3. So I know 2 is in series with 3. Is there anything else in series that I can put directly? The answer is no. Now, if 2 is in series with 3, okay, so can this be reduced to, can this circuit be reduced to, rather than showing these as two different registers, can I show, can I remove this and just put a register of resistance 2R here, and this is because 2 was in series with 3. So their equivalent resistance is R plus R equals to 2R, right? Obviously. Yes, Sandy, your answer is correct, obviously, yeah. So R plus R 2R, okay? Now, if those R plus R were 2R, now let us see, is there anything else in series? Again, no. But if you see now, these two are is in parallel with resistance number 4 for the fact that if I take only these two, right, by taking two and only these two, I can complete a loop, right? So they are a happily married couple and they are in parallel. So I can say this 2R register is in parallel with R. So obviously, if 2R is parallel with R, it would be, 2R squared by 2R plus 1R, that is 3R. So which is nothing but 2 by 3R, right? 2 by 3R. So if these two are in parallel, so if these two are in parallel, can I say that in this at this point I would remove both of them, and can I put a register of resistance 2 by 3 R. Now, if this is at 2 by 3 R, now this has become very simple, right? So 1 is in series with this piece, right? And see, now don't think that we had a different things there. So we have already made it string with by taking the equivalence resistance. Okay, so now I can say that 1 is in series with 2 by 3. So this entire combination and 1, they are in series, and again this is in series with this R also, because this is their meeting point and there is no disturbance at the meeting point. So again our happy lovers couple model applied. So all these three are in series. So I can say that your R is in series with 2 by 3 R, which is again in series with another R. So which should be nothing but 2R plus 2R by 3. So which is nothing but 3 comes in your LCM, 6R plus 2R, or the answer is 8R by 3, right? Okay, so pretty simple. So one thing which we should progressively understand that obviously though a circuit looks big, as we start finding out the equivalent resistance, it starts shrinking. Okay, fair enough. Let's move on to our next practice problem. Okay, and this one is referred as ladder problem in many reference books. Okay, so we will go into a ladder kind of a structure and see what would be equivalent resistance in that scenario. Okay, so as shown, this is the electric circuit. Okay, point A, point B. Yeah, if I ask you to find out the equivalent resistance, very simple, right? R plus R, both are in series. Now this would be 2R, okay? But assume I will add it like this, okay? Okay. Now 1, 2 are no more in series because at their junction point there is a disturbance 3, right? Okay. So similarly, let us expand this a bit. Okay, let us expand it for one more loop. Okay, and this is 5, this is 6, this is 7, this is 8. Okay, okay. Now, if this is the case, okay, now we need to find out the equivalence resistance. And let's do one thing. So let me give some numbers to this, right? So let us assume this one is 2 ohm, this one is 2 ohm, okay, and this is your 4 ohm, this is again your 2 ohm, okay, and this is again suppose your 4 ohm, this is again 2 ohm, this is again 4 ohm, and this is again 2 ohm. So let us try to find out what would be the equivalent resistance of this circuit. Again, very simple. I mean, the point is that we need to understand the concept and the trick that we are using, and obviously after that, arithmetic is not a big deal, right? So yeah. So in this scenario, the first thing that will be synced would be 7 and 8 are in series. If you see here, I'll say that 7 is in series with 8. Why? This is their meeting point. At their meeting point, there are only these two. There is no third disturbing element. But for every other point, if you see, there is a disturbing element. So I cannot say that 5 is in series with 6. Okay, but certainly 7 is in series with 8. Okay, so if 7 is in series with 8, so I can say that the equivalent resistance of them would be 2 plus 2 equals to 4 ohm, right? So if that is 4 ohm, can I remove both of these and just put one resistor equivalent to 4 ohm here, right, across those two same points, 4 ohm. Okay, now if I do that, the next part will be very simple for you. So if you see this entire part and resistor 6, okay, so this 7 series with 8, whatever is the equivalent resistance that is in parallel with 6. Why? Take only these two and you can complete a loop. Okay, so if you can complete a loop, then both of them are parallel. If both of them are parallel, can I say that their equivalent resistance would be 4 by 2, that is nothing but 2 ohm. Okay, now if that is 2 ohm, then obviously we can delete both of these 6 and the entire thing, and I can write 2 ohm there. Now again, this 2 ohm is in series with resistor number 5, so which is nothing but 2 ohm plus 2 ohm equals to 4 ohm. So I will delete both of these and put a 4 ohm resistor here because they are in series. Okay. Now again, this 4 ohm and this 4 ohm, they are in parallel. So their equivalent resistance again would be 4 by 2 equals to 2 ohm. So I can remove both of these and put just a 2 ohm resistor here. Okay. Now again, if there's a 2 ohm, again 2 ohm plus 2 ohm, again it will be 4 ohm. Okay. So if I remove both of these, then I can put a 4 ohm resistor here, 4 ohm and 4 ohm. They are again parallel. So again it would be your 2 ohm. Okay. So again it is 2 ohm. Now it is, if it is again 2 ohm, now if you see all the disturbances between this one and this entire series is gone. So now I can say one is in series with this entire thing which we have calculated. So 2 ohm and 2 ohm are in series. So the answer would be 4 ohm. Okay? Yeah, obviously it would be 4 ohm. But obviously I wanted to do it step by step. Good. Who found it earlier, faster, good. But I want just all the students to get these step by steps. Okay? Perfect. Good. Let us move on to the next practice problem. Okay? So this one we would say, okay, let us do one more small ladder practice problem, and this one I would just do it little faster than the previous one. Okay, so in this ladder problem, I have one register like this, and in this leg also let me put a register. Okay, earlier my this leg was empty. Now here I am putting registers all the way. Okay, let us just do this much. This is good enough, and you can keep repeating it to whatever number of loops that you want to do. Okay, so say register number 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm saying each resistance equals to R ohm. Okay, so suppose everything is your R ohm. So in that scenario, let us try to find out what would be the R equivalent in this case. Again, very simple. We will follow the old funda. So now I can say 7, 8, and 9. All three are in series. 7, 8, and 9. If 7, 8, and 9 are in series, so this one equivalent resistance would be 3R, R plus R plus R. Why 7 and 9 are in series? Because at their junction point there is no disturbance. Similarly, 8 and 9, while they are in series, at their junction point there is no third disturbing element. Okay, so all these three are in series. Okay, so the equivalent resistance comes as 3R. If equivalent resistance is 3R, I can remove all these three and I can just put a 3R here. Okay, so if here is a 3R and here is an R, so if you see, obviously these two are in parallel. Okay, so 6, or your R is in parallel with 3R, so R into 3R by R plus 3R. Okay, so that is nothing but obviously 3R squared by 4R, 1R, 1R get cancelled. So this is nothing but 3R by 4. Okay. Now, if these two are parallel, so I will remove these and I can put a 3R by 4 ohm resistor here. So now, this 3R by 4 ohm resistor and this R and this R. So 4 is in series with this 3R by 4, 5 is in series with this 3R by 4. So equivalent resistance of this one, and this one will be nothing but R plus 3R by 4 plus R, which is nothing but, if you take 4 as LCM, this is 4R plus 3R plus 4R, which is nothing but 11 by 4R. Correct? Okay. Now, which means I can remove all these and just put a register of 11 by 4R in this place. 11 by 4R. Now again simple, this 11 by 4R will be in parallel with this, correct? So again the if these two are in parallel, why? Again because taking all these two only, I can complete a loop. Okay, so 11R by 4 into R by 11R by 4 plus R. Okay, so yeah, so in the numerator it becomes 11 by 4 R squared. In the denominator it becomes LCM is 4, 11R plus 4R. So 4 get cancelled. 11R squared by 15R, 1R, 1R get cancelled. So this is nothing but 11R by 15. Okay? 11R by 15. So I can remove this entire stuff and I can put 11R by 15 ohm resistor here. Okay? Now again, that last step, one is in series with this, and this one is also in series with two. All these three are in series. So answer would be we just need to add all these three registers, right? So resistance of register one is R. This entire piece is 11R by 15, and this one is again R. So LCM is 15, right? So 15R plus 11R plus 15R, right? So that is nothing but 41R by 15. This many ohms. Okay? Yeah. Okay. So this is good. Fair enough. Now let us. This is good. So now let us go into the next circuit and see which one and see how we'll solve that one. Okay. Yeah. Now we will use one more small thing. So we are now kind of in the verification of few things. So now we will solve something slightly different. Okay, let us go to next practice problem. Yeah, so we are in problem number 7. Okay, now this is the problem. Okay, A and B, and this is your, say, R1, this was R2, this is R3. Okay, now this is the question. Here, if you see, you may get a deja vu that, hey, we solved this problem in problem number 1, but here is one concept that I wanted to introduce, and that's why I've shown. So in this case, the R equivalent would be R3 only, and let us understand why. Okay, while solving electric circuits, the registers or the segment of the circuit where no current is passing through, we should cut it away from the circuit, because if no current is passing through, they do nothing in the circuit. So they are just your false entries kind of thing. Okay, so and why current will not pass through? So current normally doesn't pass through a particular segment if, first thing is, if it is short circuited. Second is when it is an open part of the circuit, if that part of the circuit is not closed. And third very important thing is when it is the central limb of a balanced Wheatstone bridge. Okay, so these these fundamentals we will see a little later. But right now, I wanted to introduce the first one that is related to short circuit. Okay, so because I have introduced this additional wire, right? So let me say this is point P and this is point Q. Okay, between point P and Q, because I have established this wire, right? So remember students that, okay, if I would have put a cell here, okay, then current would have come up to this point, okay. After coming this point, current has two choices. It has one way to go into this direction and one option to go into this direction. Now you just imagine you hit a junction point while driving on a road, right? And you have two options. One road is very bumpy by nature. You see a lot of obstruction in that road. And second one is a, suppose your express highway of which is a very wide express highway. So in that scenario, would you prefer to go through the express highway or through the bumpy road? Obviously you would choose the resistance free road, right? So a road which provides you no resistance. So remember students, a circuit is called short circuited, or a segment of a circuit is called short circuited when there is an equivalence, or there's an alternate path which gives zero resistance to it. And if there is zero resistance, right, so obviously current would tend to go through that one and not through the circuit, right? None of us like resistances, and none of us like somebody to resist us or trouble us, though it's very necessary for life, but then still none of us like that, right? So just like and current is no different than us in that scenario, or in that property for that matter. Okay, so that is why what would happen, no current would flow through this circuit. Okay, so for this part no current would flow, and as I said, if no current is flowing, we can happily remove that. So if this is happily removed, right? If this is happily removed, only one thing you have got is R3. This one, as we have said, it is a short circuited path. R equals to 0. So 0 plus anything would be that thing. That's why the answer is R3. Now, here you may have a question that how I would know that this is short circuited. Remember, students, in your physics syllabus, whenever you would, uh, until and unless you see this resistance symbol or any electric device, electronic device like your ammeter, voltmeter, whatever, right? If you just have a plain wire like this, it is assumed that the resistance to this is zero, which means this intention of that one is to give the short circuit only. Okay. Now let us use this to solve one or two small problems. Okay, so that this concept will get registered even better in your mind. Okay. So let me do a small tweak to this one itself, and let's see how it will behave. Okay. So I had two resistors, R1, R2, and this one is R3. So rather than, and I want to find out the equivalence resistance across these 2 points. So these are my uh, A and B. Okay. So earlier I connected a path from here to here. Okay. Now what I would do, suppose I would just connect a path like this. Okay. If I connect a path like this, then obviously no resistance will flow through R3. Okay, so only R3 should be removed from the circuit, nothing else. Okay, so in this scenario, if I remove R3, what will be the equivalence resistance? It will be nothing. So now these two are in parallel. So the answer would be R1 R2 by R1 plus R2. Okay, Okay, so sometimes in especially in competitive exams, they may trick you with these short circuit funda also. Okay, so they will try to short circuit your brain with that. Okay, so you need to be a little watchful about that. Now, in this same example, now let me pick something else. Okay, so if you want to say that problem number 9 and 10, it's your call. Okay, so say this was R2. Okay, if I would just put uh, uh, a short circuit, say from here from here to here. Okay, so the important thing is understand where that short circuit is put. Okay, so if short circuit is put across these two things, which means no current would flow through this part, so only this part can be removed, anything else and everything else remains the same, right? Right, now if it is like this, now if you see current after coming here, okay, again it has a resistance through this part and it has a short circuit through this part, so nothing will go through this part also, so automatically even this part would get cancelled out. Okay, and then finally you would leave with only R3, and again the equivalence resistance would be R3. So these things can be slightly changed. Okay, yeah. Now, let us try to solve one more small problem related to short circuit so that it will be 100% registered in your mind. Okay, let us solve that letter A problem. Okay, you have letter A and say if I short circuit it like this, right? So if I short circuit it like this, so which means you can remove this entire segment, right? So yeah, so you can remove this entire segment. So sorry, I'm sorry. I mean, this one will be removed and this one will be removed. So only this, and this would stay. Okay, and then finally, no, even this one will be removed because this will be short circuited by this. So only this register and this register would be remaining, and the answer would be if this is R1 and if this is R2, or if this is R3, this is R2, then answer would be just the summation of these three. Everything else would be removed because this entire part is short circuited. Only this one plus this one. That's it. Okay. Now, if this is done, let us go to next problem. Okay. And again, let me take my favorite letter A. Somehow I don't know. I love letter A. It's the first letter of English. It stands for awesome. It stands for amazing. And yes, this is good. And something that comes first is always most appreciated. Okay, good. So this is your letter A again. Okay. And here again, one, two, three. Let's do the numbering. Four, five. Assume each resistance is R. I want to find out equivalent resistance across point AB. Okay, and here I have a sixth register also. I have register number 6. Okay, if I have register number 6 also, which is also of resistance R, in this scenario, what would be the equivalent resistance? Now, if I want to find out equivalent resistance across these two things, right? So I would have connected a cell across these two. In that scenario, if you see 1, 2, 3, 4, 5, so the loops wherever they are, those are closed loops. Those are closed loops from for resistors from 1, 2, 3, 4, and 5. All these are in closed loop. But resistance number 6 is not closed, right? So it's an open part, right? So if it is open, as we have studied in your point number 2, that if circuit is not closed, no current will flow through it, which means this is just a false one to unnecessarily confuse you. And then we have seen it already earlier. 4 and 5 in series, that will be in parallel to 2, and this entire thing, 1, this entire thing, and 3, all of them are in series, and you find the answer quickly. Okay. Now let us move on to something different. So we have covered two theories related to removing segments where current is not passing through. Intentionally, Wheatstone bridge I am not covering in this session. We'll be taking up in a different discussion. Or it would be too much of information to digest in one shot. Okay, but then now let us come to some interesting practice problems which I have noted here, and I think yeah, let's get started. Okay, now let's go to our problem number 12. Okay, and let us make a little more geometry. So let's make a hexagon. Okay, okay. So here's the resistance. Okay, and then we have resistance here, then something here, then a resistance here, then a resistance here, and suppose maybe one more loop, right? Okay, and yeah, you want to keep one more here. Please go ahead. So we have one, two, three, four, five, six, six, seven, eight, nine registers. Okay, and what we want to do, we want to suppose, we want to suppose find out the equivalence resistance across these two. Okay, so if you see, in reality, just the geometry is different, but this is exactly like your ladder problem, right? Why 9 and 10 are in series? Sorry, 8 and 9 are in series, because if we go to the meeting point, there is no issue, right? So 8 is in series with 9, right? Then this entire thing is in parallel with 6. Why? Because if I remove both of these and if I put just one register here, that one and 6, they are a happily married couple. You can complete a loop with them. So they are in parallel. Now, this entire thing, whatever is their equivalence resistance, right? So this entire thing again would be in series with 7. Okay, and if this is in series with 7, why? Because again, at the junction point there is no third connection. If these two are in series, you can remove both of these and just put that one resistance here. This entire stuff is in parallel with 5. Suppose again this one is parallel to 5. If these two are parallel, because by taking this one and this one we can have a closed loop, right? So if these two are parallel, we can just put whatever is this value here, and this one and 4 are in series. That entire thing will be in parallel with 3. Similarly, this thing will be in series with 2, and entire thing will be in parallel with 1. So step by step, by doing the arithmetic, you can solve this problem too. Okay, so anyways, I don't want to spend a lot of time on this one, but now let us start getting into one more concept. So let me pick up the right example for that. Okay, so let's get going. Yes, yes, we have it here. Okay, now, okay, now let me take a rectangle. Okay, so here suppose I have for instance R1, instance R2. I have one more register here. I have one more register here like this. And now let me connect one of the diagonals. Okay. And here if I ask you what is the equivalence resistance across these 2 points, A, B. Again, my intent is obviously not to teach you arithmetic, so I don't mind giving the values to them. So in all my examples hereafter, Wherever I'm not giving, assume that the resistance is R1. Okay, so say this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So if these are, 6 registers like this, right? And I'm asking what is the equivalent resistance across points A and B? Again, very simple. 2 and 4 at their meeting point, there is no obstruction, so they are happy, lovers couple. So 2 is in series with 4. So you can find out that obviously it would be R plus R. So I leave that arithmetic part to you. R plus R obviously would be 2R. Okay. So find out the addition of these two. After these two are in series, right? Then I can say whatever is the equivalent resistance, right? So whatever is this, with that and this one, I can make a closed loop, right? So this one is in parallel with 3. Okay. So I can remove these two. This is parallel with 3. Okay. And then in this scenario, 1 and 3, they are in series because at their meeting point, there is no obstruction. So rather than saying 1 and 3, I can just put one register like this here directly, right? And in that scenario, this one would be in parallel to this. So you can apply the same parallel formula and find out the equalizations. So this part is pretty simple. This part is pretty simple. Now, let us make this problem a little complicated. Okay. So we will make this problem slightly complicated. Okay. So what we will do, suppose this is the situation where we are, and let us rather do it like this. This is one diagonal. Suppose I have other diagonal also, right? In this scenario, and let us number them: 1, 2, 3, 4, 5, and 6. And I want to find out the equivalence distance across points A and B. Now let us try to find out. All right. In this scenario, if you see, okay, can I say that 1 and 2 are in series because this is their meeting point, right? But if you see, this meeting point is connected here to your point. So I cannot say that 1 and 2 will definitely be in series, right? Similarly, between 2 and 3, are they in series? No. At this point, there's a disturbance, so they cannot be a happy, lovers couple. There is some disturbance here. Okay. Similarly, between any two resistors, if you see in this entire circuit, none of them are in series. Okay. Similarly, yeah. So probably we can say that initially 3 and 5 are in parallel, and 1 and 4 are in parallel. So that's fine. It looks like that, right? But there are a lot of disturbances in this, what you say, problem. Okay. So to solve this, what we normally do is, okay, we go to one more smaller concept. Okay, which indicates that we have discussed that any segment of the circuit through which electric current is not passing, we can we can cut out that and throw that out from the circuit. Now let us see how would I redraw this circuit. Okay, so if this circuit is like this, right? So uh, suppose I'm an electrician. Okay, so can I make a circuit like this? See, I have not changed any register. All that I have done is this was connected like this, right? So all that I have done is I have just done it like this. Okay, that is all I have done. Okay, that is all I have done. So rather than the meeting point here, I have made this meeting point like a wire. So it doesn't matter, right? So you know that even if you hold a small wire and put into a phase of an electrical point, you will get shock, or if you use a long wire also, you will get a shock. So it doesn't matter whether it's connected like this or like this. Okay. So to solve these kind of problems where we cannot find series and parallel easily, okay, what we do, we use a technique called battery technique or battery use technique, okay, or cell use technique. Okay, so what do we do? Let us connect an imaginary cell to this. Okay, so if I connect an imaginary cell to this, right? So current would start flowing, right? So in this direction it would come up to here. Then somehow it will, go through this circuit, and finally, the same amount of current would come out, which we will study in detail in Kirchhoff's law. Okay, we'll park it till that discussion. But how do we solve this circuit? So in this scenario, if you see, in this scenario, if you see, let us analyze this point. Okay, so say some current, some current some current I1 came here, okay? So that would have got divided into two parts, right? This part and this part. Some I2 and some I3. See, both these have some resistance, so resistors, so current will get divided. If suppose I put a short circuit path, then this entire circuit you can throw away. This is useless, okay? But there is no short circuit. You have resistors in all the paths, okay? So which means current will get divided. Similarly, using the symmetry, I can say that some current would have come here through this, okay, 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 and after that, what we do is I say reverse the cell, okay. If you reverse the cell, it will be like this, right? If you reverse, then a similar thing would come here, one, two, right? And 3. Okay, but remember, whenever you are going with your DC circuit, cells are not reversed. Okay, why I have drawn this reversal is it will be easy for me to understand the direction of current, which means the I2 which is coming through this, the same I2 would have come here. The I3 which is coming from this side, the same R3. Now I'm changing back the directions again. Okay, so I'm just now changing back the directions. Okay, so which means some I4 which would have gone through this, same I4 would come through this part. Okay, and I5 which has come up to here, the same I5 would go through this. Now if you see, now if you see current, oh sorry, just one more, sorry. Okay, so current coming from this side is I3 and going to this side is I3. From this side is I4, going to this part is I4. So, is there in reality any current flowing through this junction? The answer is no, right? So, let me, zoom it for your understanding. Okay, this is like this. So, here the resistance, and here it was, right? So, and I3 was coming in this direction, okay, and that same I3 was going back like this, came like this, went like this, right? Similarly, an I4 came like this and went like this, right? So if I4 came and went like this, then is there any current, is there any current through this segment? The answer is no, because I3 came and went from there, I4 came and went from there, which means this part, no current is flowing through. So, which means I can happily remove it. Okay? And if I remove it, then you would see your circuit will become very easy. Right? So, if I remove it, and let me erase the not required portions. Okay? So, you have an over here, register here, and a register was here, right? Now if you see, now things are pretty simple. This one is in series with this one, okay? After these two are in series, the entire combination is in parallel with this, okay? So I can say that Now, if all are R, right? So this is R, this is R, this is R. So R and R series, that is nothing but 2R. This 2R is in parallel with this R. So this is nothing but 2R into R by 2R plus R. So answer is, so that is nothing but your total 2R by 3. Similarly, for this segment also, it would be 2R by 3. Okay? And if this entire segment is 2R by 3, and this entire segment is also 2R by 3. So it's very easy to comprehend that these two are in parallel because they are a happily married couple. You can complete a loop with them. So these two are in parallel, and that's why it would be, you can just do a by 2 here. So 2 cancels out, and so would be R by 3. Okay, fair enough. So I think let us move to the two last problems of the day. So we'll solve two more circuits and we would put a logical pause there. Okay. So yeah, let's move on. So let us try to solve this circuit. Okay. So I want to draw a triangle. I have drawn a triangle. Okay. And then, okay, let me draw it little bigger. So I have a triangle, and then I have connected three more registers like this. So again, let me name them: one, two, three, four, five, and six. Okay, and I want to find out. I want to find out the equivalence resistance across these 2 points. Okay, equivalence resistance across these 2 points. So, and again, assume every resistor is carrying a resistance R. Okay, in this scenario, how we will solve it? Okay, if you see here, 1 and 6, 1 and 6, are they in series? No. 6 and 5, are they in series? No. So if you see in this circuit again, you will come up with the same problem. It's not very easy to define or identify which are in series and which are in parallel. So we will use the same technique. Okay. So and again, students, this can also be solved with which balance Wheatstone bridge. So that is another technique, but this technique I find is a little easier than balance Wheatstone bridge. So we'll go to balance Wheatstone bridge in due course of time. Okay. So now here if we see, suppose if I connect a cell here. Okay. If I connect a cell here, current would start flowing like this, correct? So say this is I1, say this is I2, say this is I3. Okay. So I1 will reach here. Okay. So after I1 reaches here, okay, after I1 reaches here, it would come down like this here in this direction, okay, and some part of the current would go in this direction, okay. So say let us call them as I4, just this much. So we have come to the half part of it. Now let us go to the next segment, okay. So if I go to the next segment, so uh, the same I1 would flow through this one, I2 will flow through this one, and I3 will flow through this one, right? But this will happen only when I would have reversed the cell. But we are actually we are not empowered to reverse the cell. So if I would put the original cell only, then I would reverse the directions, right? So like this one I would put back like this, and this one I would put back like this. Okay. So if I3 is coming, I3 goes back like this. Okay. So I2 came and went back. I1 went here and I1 came back here. So in this scenario, if I1 came here and I1 went like this and I1 came back like this, I2 went like this and I2 came back like this, right? So is there any current flowing through register 6? The answer is no. Okay? The answer is no. And if there is no current flowing to register 6, I can happily remove register 6. It's useless, right? So it's a dummy one. Okay. So I can remove register 6. And if register 6 is removed, then this circuit becomes very, very easy. Right? Okay. So then it becomes very easy. So 1 is in series with 5. So R plus R, 1 is in series with 5. So R plus R, 2R. Similarly, uh, yeah, these two are also in series. So these two will also be 2R. Okay, and this is R. And if you see, if these two are in series, I can remove both of them and just put one register, that is 2R. I'll remove both of these and just put a register R, sorry, 2R, and this is 3. Now this is 2R, this is 2R. Just by taking these two, I can complete a loop, which means they are in parallel. So if they are in parallel, I can remove both of these 2Rs and I can just place an R here. This R and this R, they are again in parallel. So the equivalent resistance will be R by 2. Okay. So normally folks use Wheatstone bridge. So intentionally, I'm not using balanced Wheatstone bridge for this. So yeah. Okay. We'll look into problem later. Okay. Now let us work out one more problem. Okay. So okay. So we will do this circuit. Okay. So I'll use a hexagon. Okay. And here. Okay. And we will complete this hexagon. Okay. And say, and then say, let us, what do we do? We'll join two of its diagonals. I'll use one more instead. Okay. Okay. So this is the circuit, and I want to find out the equivalence resistance across these 2 points, A and B. Again, assume each register carries R ohm, and let us do the numbering. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So what would be the equivalence resistance in this case? Okay. So if you followed the previous two examples, properly, this will be again very easy for you. Okay. So first thing, I am seeing a junction point here. So I would redraw the junction point. Okay. I would redraw the junction point like this. Okay. So which means effectively I have not changed anything in the circuit, in this circuit. Then let me connect a cell here. If I connect a cell, Then let us, try to find out what ideally should be the current distribution. So suppose a current I1 goes through this, a current I2 comes to this part. Okay. So when it reaches this node, right? When it so and say after reaching this node, it would again get divided. So say this is I3, say this is I4. Okay. Similarly, after reaching this point, this current I2 will also get divided. So say, let us call them I5 and I6. So we have reached half part of this circuit, stop and then reverse the cell. Now reverse the cell, if I reverse the cell from the other side, okay, so it will be I1 from here, I2 from here, similarly I5 from here, I6 from here, your, I1 is coming, so I2, I3 is coming from this side, I4 is coming from this side. So this is it. But we know that we are not empowered to change the cell position. So if I go back to the original cell, I need to just change the direction of the things which I did at the end. Okay. So I4, it will be like this. I3 is like this. I1 actually is like this. I2 is going back into be like this. I5 is going like this. I6 is also going like this, right? So if you see here, see, and let us see if this is logical or not. You got, I2 got divided from here, it came here, it became I5 and I6. So after I5 and I6 got added, again it became I2. So this is logically correct. Similarly, your I1 was here, that got divided into I3 and I4. So finally, when I3 and I4 are meeting, this is has again become I1. So that is also logically correct. Now, if this distribution is logically correct, I3 came from this side, I3 went like this. I5 came like this, I5 went like this. So, which means what is the current through this segment? That is nothing but zero, right? In this segment. If in this segment current is zero, can I remove this segment? The answer is yes. I can happily remove this segment. If I remove this segment, it again becomes very easy. Okay. So that's why I was saying, right, that electrical circuits are like your leeches. They would shrink very quickly if you put the right amount of salt. Okay. So now things are very easy. So I can say that, okay, I have kind of missed out the initial numberings. So I would give the numberings again. Let me remove the current because their use is done. Okay. It will easy make things easier. I'm removing the currents because we have already made whatever they were introduced for. Okay, so this is one, this is two, this is three, four, five, six, seven, eight, 9 and 10. Yes, so all the registers are here, right? So can I say 2 and 9, they are in series. 2 is in series with 9. So that is nothing but your 2R, right? Similarly, 3 and 6 are in series because at their junction point, there is no disturbance. They are happy, lovers couple. So they are in series. So I will remove 3 and 6 and I would just put how much? 2R. I would remove 2 and 9, and by removing 2 and 9, I would just put 2R. Okay. Now if you see, this 2R is in parallel with resistance number 10 because taking these two, I can complete a loop. This is a happily married couple, so they are in parallel. So 2R into R by 2R plus R. So that is nothing but 2R by 3. So which means I can remove both of these, and in this place I can just put a register that is equivalent to 2r by 3. Similarly, here also I can remove both of these and I will substitute it with 2r by 3. Okay, now if you see, one is in series with this because at the junction point there is no disturbance. Okay, so similarly to this and 8 are also in series because this is the junction point and there is no disturbance. Similarly, 4 is in series with this, which is in series with 7. So for the upper segment, it would be this portion and register 8. They are in series. So 1, so this is R plus 2R by 3 plus R, right? So which is nothing but 3 comes as a LCM. So this is 3R plus 2R plus 3R, which is nothing but your 8R by 3. Okay, so which means I can remove this entire part and put 8R by 3 here. Similarly, same calculation for this part. I can remove this entire thing and put 8R by 3 here. 8R by 3, 8R by 3. Again, these two are happily married couple. By taking these two, you can complete a loop. So they are in parallel. If they are in parallel, then 8R by 3 by 2. So 2 and this becomes 4. So the answer is nothing but 4R by 3. Okay, 4R by 3. So you see how a big and complex looking circuit has got shrinked to smaller ones. Okay, so students, we would take a logical pause here. uh, so if you ask me, are we done with all the geometries and all the things, the answer is no. There are obviously many more tricks, there are obviously many more problems to solve. But then considering that we have spent 90 minutes, I think we'll take a logical pause here. So class 12 students, so continue your tomorrow's class, which is at 5:30 p.m. So in that class we will be discussing some more problems and we'll try to understand it even better. Thank you students, you have a good time. Bye bye.